talking about linear systems today, which is section 3.1. So last class, we learned that this is what a linear system looks like. It's a system x prime is ax plus by, y prime is cx plus dy, and we learned how to write that using a matrix notation. And one of our big conclusions from last class was that this system will always have 0, 0 as an equilibrium point. And the only way it can have an equilibrium point other than 0, 0 is if what? Close, yeah, you kind of are remembering. AB minus C, wasn't it AD minus BC? AD minus BC has to be 0. This is the only way we have non-zero equilibrium solutions. So that was our big conclusion. 0, 0 is always an equilibrium solution. And the only way we could have another non-zero equilibrium solution is if the determinant of the matrix, which is AD minus BC, is 0. Okay, so that was our big conclusion from last class. We spent some time talking about linear systems as models. And we learned this notation, this matrix notation. This was our big conclusion. And that was really it from the first half of 3.1. So the most important property of a linear system is the linearity principle. So suppose we have a linear system of differential equations. If you have a solution to this system, and k is any constant, then k times the solution is also a solution. So if you know a solution, you can generate infinitely more solutions just by multiplying by a constant. And if you happen to know 2 solutions, you can add them together and get another solution. Okay. So if we put these 2 together, right, these 2 statements combined into one statement, it says that if you know 2 solutions and you have 2 random constants, then k times y1, k1 times y1 plus k2 times y2 is also a solution. So that's called a linear combination. When you add 2 things together, a multiple of 2 things, add them together, that's called a linear combination of the 2 solutions. So if you happen to know 2 solutions, you can generate infinitely many more of them, infinitely many more solutions by taking linear combinations of the 2. So all of this rests on knowing 2 solutions. If you happen to have 2 solutions fall in your lap from the sky, right, then you can generate any number of solutions you want by taking linear combinations of the 2 you know. Yeah. Yeah. If what's not dependent on y? Oh, nope, it can be dependent on y. Yeah. Any system of differential of linear equations. So you got to keep in mind that when I write these things in bold, that's a vector, right? So y of t in bold, just remind you, that's the vector x of t, y of t. So maybe that's what's confusing you? Okay. So when I write bold y of t, that's a solution to the linear system, meaning it's 2 functions, an x of t and a y of t, that make the linear system true. And when you multiply a vector by a constant, So if I do k times y of t, that means k times x of t, y of t, which is k times x of t, k times y of t. Yeah, please stop me if there's ever notation things like that, because it's easy for me to forget that everybody's not familiar with the matrix notation. All right, so here's a linear system. Y prime bold, which means that is really x prime, y prime as a vector, is equal to 2, 3, 0, negative 4 as my matrix A, times the vector y, which is really x times x and y in a vector. So I could rewrite this. Xy is equal to 2, 3, 0, negative 4. Sorry, this is x prime, y prime times xy. And then I could do matrix multiplication to separate this out into two distinct systems, if that's more comfortable. So I would write x prime equals, you take the 2, 3, right? The first row of the matrix, flip it on its side and lay it on top of the xy, and you get 2x plus 3y. And then you do the same for the 0, negative 4 row on top of the xy, and we get y prime is 0x minus 4y. So that's the system represented by this matrix. They say the same thing. Now, in section 2.4, we solved this system of equations. This is partially decoupled. So we spent a good amount of time learning how to analytically solve it, and we came up with two solutions. They're here. So y1, that says that x of t is e to the 2t, and y of t is 0. That's one set of solutions, an x and a y, that make this system true. And then we have another set of solutions that also make that system true. Because we know for any differential equation or system of differential equations, there's infinitely many solutions. We happened to have found two by using one of our analytic techniques, because those two equations are partially decoupled. Okay, so we've got two equations. We want to verify that they are actually solutions. So rather than going through the whole process of deriving them, we just are going to plug them in and see if they make the equation true. So I'm going to do it all using matrix notation, because we have done this where we have plugged into the two systems. I want us to get more comfortable and familiar using the matrix notation. So I have y prime. When I write on the board, I'll use the little arrow to indicate a vector, because making the bold is a pain. 2, 3, 0, negative 4. Okay, so that's my system, and my y1 was e to the 2t 0, and y2 e to the negative 4t and 2e, negative e to the negative 4t. Okay, so now I want to show that these things are true. I want to show that y1 and y2 make this equation true. So what I need is y1 of t prime. So if I take the derivative of y1, I'm just going to take the derivative of the components of the vector. So this one, the derivative of e to the 2t, would be 2e to the 2t. And the derivative of 0 is 0. Okay, so that's the left side of my system. And then the right side says that I need to multiply this matrix times my vector e to the 2t 0, and I should get this. Okay, so now I'm going to do my vector my matrix 2, 3, 0, negative 4, times my vector y1, which is e to the 2t 0. Yes, that's exactly what we're doing. So I'm going to multiply this using matrix notation. Hopefully I get the same thing I get when I took the left side of the equation, the derivative. Okay, so I do my 2, 3, pick up the whole row, turn it on its side, put it on top of the vector, and I get 2e to the 2t plus 3 times 0, which is 0. And then I do the 0, negative 4, pick it up, and I end up with 0 times e to the 2t, which is 0, plus negative 4 times 0, which is 0. So you can see when I plugged into the left side, I get the same vector as when I plugged into the right side. So it actually takes quite a lot less work to check solutions if you use the matrix notation. So get comfortable with it now while we're still in 2 dimensions. Okay. All right, so let's check y2. Actually, why don't you check y2? Take a couple minutes in your groups, verify that y2 is a solution. Okay, so I'm going to take my y2 and I'm going to plug it into this matrix equation. Okay. So y2, what I'm going to do is I'm taking y2 and I'm going to plug it in here. I want to check, does y2 prime equal 2, 3, 0, negative 4 times y2? We want to know if this is true. Okay, so I take y2 prime. To take the derivative of a vector, you just take the derivative of each component. So this is going to become 4e to the negative 4t. And the derivative of 2e to the negative 4t would be negative 8e to the negative 4t. And we want to know, does that equal 2, 3, 0, negative 4 times my vector that represents y2, which is negative e to the negative 4t and 2e to the negative 4t. So we're trying to see, is this equation true? When I multiply the matrix times the vector, do I get this vector, which is the derivative? So to multiply matrices, multiply rows times columns. So you take your 2, 3, pick it up, turn it on its side, lay it on top of the vector, and we get negative 2e to the negative 4t plus 6e to the negative 4t. Okay, so you have the 2 matches up with the first component of the vector, the 3 matches up with the second component of the vector. You multiply the parts that match up, and you add them together. Right, so then we do the same thing with the second row, the 0, negative 4. So I end up with 0 on top of the first component of the vector, so I get 0. And then the negative 4 is on top of the 2e to the negative 4t, so I get negative 8e to the negative 4t. Does that equal the derivative vector? Yes. Negative 2 plus 6 does give me 4, and 0 minus 8 does give me negative 8. So these are the same. All right, good. So we're getting more comfortable with the matrix notation. Can verify that given solutions are in fact solutions. Now, the linearity principle, the most important principle of linear systems, was the linearity principle that says that any linear combination of two known solutions is also a solution. So we had two solutions, y1 and y2. I should have written those down again too, sorry. y1 of t was, somebody read it back to me? E to the 2t and 0. And y2 of t okay, so I have two solutions, which means that any linear combination of those two solutions should also be a solution. So I picked a random one, right? I picked some random coefficients, negative 2y1 plus 5y2. That's a linear combination of y1 and y2. Verify that that is also a solution. Okay, so let's do the verification together. So first we had to come up with the actual vector that is y3. So we just had to do a little bit of vector arithmetic. When you multiply a constant times a vector, you multiply every component by that vector. When you multiply, every component by that constant. And when you add two vectors, you add them component-wise. Add the tops, add the bottoms. So we came up with the vector that is y3. So the claim is that this is a solution to the system, because this is a linear combination of two known solutions. Okay, so we have y3 equals that vector. We want to know, does y3 prime, does that equal my matrix times y3? Okay. So y3 prime we get by taking the derivative component-wise. So take the derivative of each component and we get negative 4 e to the 2t plus 20 e to the negative 4t is my first component. That's the derivative of the first component of y3. And then the derivative of the second component of y3 would be negative 40 e to the negative 4t. I need a little more room. I should have done this somewhere else. There we go. Okay. So does that equal my matrix 2, 3, 0, negative 4 times my matrix, my vector that is y3, this messy thing, negative 2 e to the 2t minus, thank you, and this one, okay. So I have to do this matrix multiplication on the right and see if it equals the derivative on the left. Okay, so matrix multiplication, take the first row, the 2, 3, multiply it by the vector, and add them together. So you take the 2, 3, lay it on top of the vector, multiply the pieces that match up, add the two together. So we're going to have 2 times this first entry of the vector y3. So I have negative 4 e to the 2t minus 10 e to the negative 4t. So that's what I get when I multiply the 2 times this first component. Then I have to add what I get when I multiply the 3 times the second component, which is 30 e to the negative 4t. So then I do that same process again using the 0, -4 as my next row that I multiply by the column vector. So when I do 0 times the first component, that's just 0. And then I add -40 e to the -4t. Right, so I taking my 0, -4, pick it up, turn it on its side, lay it right on top of this vector. The parts that match up, you multiply, and then you add the two products. Okay, so this resulting vector, does that equal the derivative vector on the left-hand side of the equation? It does, because this term and this term combine to make our 20 e to the -4t. All right, so rather than prove the linearity principle, we just did one example to show that it was true. And the proof works just like the example, except instead of using specific solutions, you have generic x's and y's. So you could muddle through the proof on your own if you want, but it looks just like the example. There was nothing special about this example that made it work. Question? For there to be no solution? So one of the things we talked about in the last chapter was existence and uniqueness. So that theorem said that as long as the right-hand side of your differential equation is nice, right, meaning continuous, then the solution exists. And if the derivative of the right-hand side is continuous, then that solution is unique. So for linear systems, because the right-hand side is linear, that's nice, always continuous. So we're always going to have solutions, unique solutions exist in the linear case. Yep, that's the proof. Well, no, because we have two specific solutions also. The general solution, yeah. That's the question. Is that the general solution? It is. Yeah. How do we know? We'll see. We'll see. So this is just a little visual to our system. So the two specific solutions that we found using separation of variables, because it was partially decoupled, those two y1 and y2 solutions that we started with are this one and this one. Those are straight line solutions. So you notice that they are actually special, right? Those are the only two straight line solutions. And all the other solutions don't look like that. Those are atypical. Okay. So they're both straight lines, which are not typical solutions to the system. We're going to learn how to exploit these straight line solutions in the next section. So just keep that in mind. So every other solution that I could draw in here, this one or this one, right? Any other solution that I can draw is a linear combination of those two straight line solutions. Okay, so we can use linearity to solve an initial value problem. So I want to find the solution y of this system that has an initial value 2, -3, right? Remember, that means x of 0 is 2 and y of 0 is -3. So I have two solutions. I have y1 and y2. I want to check if either of those satisfy my initial condition. So let's try y1 of t, which was 2e to the 2t. I don't know, just e to the 2t, okay. 0. And y2 of t, which is -e to the -2t, and 2e to the -4t. Oh, thanks. Okay. I want to check if either of these satisfies my initial condition. If I plug in 0 for t, do I get 2, -3? Because if I do, then I'm done. I can just say, oh, that's the solution that satisfies my initial condition. So if I plug in a 0 here, I get 1, 0, right, which is not 2, -3. So that's y1 is not the solution that satisfies the given initial condition. y2 of 0, that would be a -1, 2, which is not 2, -3. So neither of the two solutions I was given or found a couple weeks ago satisfies this initial condition. But I know I can generate more solutions by taking linear combinations of the two that I know. So I know that I can take some other y3 to be k1 times y1 plus k2 times y2. And I want to choose these, my k1 and my k2, so that y3 of 0 gives me 2, -3. So I want y3 of t to be k1 times, I'm going to write in the functions here. No, it was just e to the 2t. Is that right? Or is it positive 2? Okay. And I want to choose this so that y3 of 0, that would be k1, times e to the 0, that would be 1. And here I get -1, 2. I want to choose my k1 and k2 so that when I do this, I get the correct initial condition, 2, -3. Is there a k1 and k2 that I can use to make this work? Yeah, how'd you come up with that, John? Yeah, so we make two equations. So this says, I'll write it all out since we're not all used to vector arithmetic. So this says k1, 0 plus -k2, 2k2 has to equal 2, -3. And then when you add vectors, you just add them component-wise. So this adds to k1 minus k2, and 0 plus 2k2 is 2k2. And then for two vectors to be equal, their components have to all be equal. So I have two equations. I have k1 minus k2 has to be 2, and 2k2 has to be -3. And now we just have a simple system of equations to solve, right? So k2 has to be -1.5, which means k1, when I plug that in here, has to be 1/2. So I found two constants that I can use to make y3 have the appropriate initial condition. And we know y3 is also a solution to the system because it's a linear combination of known solutions. So my final solution was y3 is going to be -2 a half y1 minus 1.5, positive 1.5. Oh, thanks. And then I could actually do this out and get a vector that shows my x of t and my y of t. So this says 0.5 times y1, which is e to the 2t, 0, minus 1.5 times y2, which is negative 2, e to the negative 4t. What's this one? 4, negative 4? Is that right? All right. So now you multiply the constants. To multiply a constant times a vector, you multiply every component by your constant. So this becomes 0.5 e to the 2t. This becomes 0 minus negative 1.5 e to the negative 4t. It's not, I haven't distributed the negative yet, that's all. I left it outside. And then 1.5, I probably should have. It's clearer. And then I end up with negative 3 e to the negative 4t. And then you just add them component-wise. Add the tops, add the bottoms. So this becomes 1/2 e to the 2t plus 3/2 e to the negative 4t and negative 3 e to the negative 4t. So there's my x of t, y of t, my two functions that satisfy my system, and the given initial condition. So the question is k1, y1 plus k2, y2 the general system to any linear, sorry, the general solution to any linear system? And it certainly seems so, right? Like you already drew that conclusion. Because we can use that general formula to solve an initial value problem. And it turns out the answer is yes. That is the general system, as long as y1 of 0 and y2 of 0, that is your initial conditions, are linearly independent. So if you've had linear algebra, you know what that means. If you don't, geometrically, it means that the two vectors don't lie on the same line. If you were to plot them both, they can't be on the same line through the origin. Algebraically, it means that one is not a multiple of the other. So if you remember, y1 of 0 was 1, 0, and y2 of 0 was negative 1, 2. If I were to plot both of these, 1, 0 looks like this, and negative 1, 2 looks like this. So they're not on the same line, right, through the origin. They don't lie on the same line through the origin. And one is not a multiple of the other. So if y1 of 0 were 1, 1, and y2 of 0 were 3, 3, we would say not linearly independent, right? They're multiples. And if we were to plot them, they'd both, one would just be an extension of the other. One would just be longer. Okay, so as long as your initial conditions are linearly independent vectors, that's going to be your general solution. So this is really good progress towards being able to solve a linear system. All we need to find a general solution are two particular solutions with linearly independent initial conditions. So we call them, we need two linearly independent solutions. So the next step is that we have to find a way to come up with those two linearly independent solutions. So that part is a little bit harder, but once you get two, whether it's by magic or some analytic method, once you have two, you have all of them. Question?
Is there like a case when you would have solutions that were on the same action? Like, I mean, it's just the same.
Right, yeah. So when you try to get the general solution, you don't get anything new. Yeah. All right, so here's a little practice I'm going to have you do in your groups. We have the undamped harmonic oscillator. I'm going to walk you through the process. This walks you through the process of coming up with the general solution.